In this video, I'm going to be talking about how to solve linear homogeneous recurrence relations with constant coefficients. First, I'm going to explain what this phrase even means. Then I'm going to show a method for solving these relations. And at first, this method probably will be a little confusing. It'll be unclear why it works. And I was unsure of why it worked the first time I saw it. And so I investigated a little further and found some explanation behind the workings of this method using linear algebra. And so I will also present this background and justification for the use of this method. But let's get started. So the first question is, what is a linear homogeneous recurrence relation with constant coefficients? So it's going to look something like this. It's going to be a sub n equals c1 times a sub n minus 1 plus c2 times a sub n minus 2 plus dot 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 c sub m times a sub n minus m. So what is this saying? It's saying that given a number of terms in the sequence, which is a sub n minus 1, a sub n minus 2, all the way down to a sub n minus m, knowing all of those terms, it's possible to compute the next value in the sequence. So let me give an example. And by the way, c1, c2 through cm, those are all just constant numbers. So the best way to understand what's going on here is to give an example. And a famous example is the Fibonacci sequence. This is given by the relation a sub n equals a sub n minus 1 plus a sub n minus 2. And you also have to specify initial conditions, because otherwise you need enough to kickstart like a process that allows you to compute the next value onto infinity. So in order to do this, you first need two consecutive terms, a sub n minus 1 and a sub n minus 2. Then you can compute a sub n and continue from there. So for the Fibonacci sequence, the initial conditions are a sub 0 equals 0 and a sub 1 equals 1. So what do you do with this? A sub 2 equals a sub 2 minus 1, which is a sub 1, plus a sub 2 minus 2, which is a sub 0. That's 1 plus 0, which is 1. Then a sub 3 equals a sub 3 minus 1, a sub 2, plus a sub 3 minus 2, which is a sub 1. And that's 1 plus 1, which gives 2. And then going on from there, you would do a sub 4 equals 2 plus 1, which is 3. A sub 5 equals 3 plus 2, which is 5. A sub 6 equals 5 plus 3, which is 8. And you can go on forever like this using the numbers that are presented. And so now the question is, what does it mean to solve a linear homogeneous recurrence relation with constant coefficients? A solution would mean something that allows you to compute a value for a sub n without knowing all of the terms that precede it. And this is called an explicit formula for a sub n. The explicit formula for the Fibonacci sequence is a little bit complicated, but we will come back to that and eventually solve it in using a couple of different methods. But let's first do some simple examples using a method that I'll first just tell you that it works and then come back to explaining why it works. So let's essentially the method that you want to use is assume that there's some number alpha such that a sub n equals alpha to the n for all n. You just assume that there's some number like this. This is meant to be an alpha. It's kind of poorly drawn. But if you know this is true, then a sub n, you can rewrite this equation here, and you would have alpha to the n equals c1 times alpha to the n minus 1, because alpha to the n minus 1 is a sub n minus 1. And just continuing this pattern here, we go all the way down to cm times alpha to the n minus m. So you assume that there's some alpha like this. And then you can solve this equation for values of alpha that could work. And you do this, it'll look something like this, alpha sub n, and then you want to just move all the terms to the left side. So it would be minus c1 times alpha to the n minus 1 minus dot 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 minus c sub m alpha to the n minus m, and this all equals 0. Then you can factor out, and you can say alpha to the n minus m times alpha to the m minus c1 alpha to the m minus 1, and then minus dot 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 minus c sub m, and there's no more alpha to the n minus m, that's fully come out, and this equals 0. And then you have a polynomial equation, and you can solve for values of alpha that allow this to be true. One solution which is always present is alpha equals 0. From right here, you usually ignore that. And you can come up with other solutions using this polynomial right here. I will be doing examples of this where it'll be clear, but essentially this assumption that there's an alpha to the such that alpha to the n equals a sub n for all n, what came kind of out of the blue. It was just being optimistic and hoping it would work. And typically, using this method, you can then test your values of alpha that come out of solving this polynomial equation. And usually you can just try to plug it in and see, you can check the given values of a sub n. So maybe you're given a sub 0 equals 2, and you're probably also given some other value because you need m initial conditions if you want to compute any values using the recurrence relation in the first place. And so suppose you're given a sub 0 equals 2, any value that you plug in of alpha will definitely fail this, because it's supposed to be that alpha to the n equals a sub n. A sub 0 should equal alpha to the 0, but any value of alpha to the 0 power will give you 1. And so it won't work with the initial condition regardless of what alpha you have. And essentially any individual solution to this polynomial equation is not going to work. But then instead of just giving up at that point, what you do is you look for a linear combination of the values of alpha. And specifically, there's a system of equations you can solve, and in the end, you should find that a sub n actually equals some new, let's do the different letter for different constant coefficients, some d1 times alpha 1 to the n power plus d2 times alpha 2 to the n power. And you should again have several solutions for alpha, and I think it should be, m solutions. So let me actually, you would have d sub m alpha sub m to the n power, and this will somehow work. I will definitely be giving examples which demonstrate this. This is a rather abstract presentation of this method, but somehow this method works. You just guess that there's some alpha such that a sub n equals alpha to the n for all n. You plug that in, you get a polynomial equation, and you get several solutions. None of them work directly, but some linear combination of them is always going to give you a sub n, and that's your explicit formula, where you don't need to know a sub n minus 1 and a sub n minus 2. You just need the values of alpha, which you solve for using a system of equations, and then given any value of n, you can just plug it into this and find a sub n without knowing the preceding values. So let me give an example of this, which makes it more concrete. And I'll keep it to a small number of terms, just 2 in the recurrence relation, so that it's not super complicated. Sorry for all the shaking in the video. Okay. So let's do this example. Say a sub n equals 7 times a sub n minus 1 minus 10 times a sub n minus 2, and we are given that a sub 0 equals 2 and a sub 1 equals 1. So recall what we're doing here is we're assuming that there's some alpha such that a sub n equals alpha to the n power. So in this case, that's going to let us say that alpha to the n equals 7 times alpha to the n minus 1 minus 10 times alpha to the n minus 2. And then we can move everything to one side and say that alpha to the n minus 7 times alpha to the n minus 1 plus 10 times alpha to the n minus 2 equals 0. We can pull out alpha to the n minus 2, and then it's going to be alpha squared minus 7 alpha plus 10 equals 0. And that's equal to alpha times alpha to the n minus 2 times, and then you can factor this, it's going to be minus 5 and minus 2, so alpha minus 5 times alpha minus 2 equals 0. And so the solutions here are alpha equals 0, alpha equals 5, and alpha equals 2. So we can now check a sub 0 is supposed to equal 2, and this is exactly the example I gave earlier. 0 to the 0 power. So it's somewhat controversial, but in general, it's only the limit that doesn't exist. 0 to the 0 equals 1, 5 to the 0 equals 1, 2 to the 0 equals 1. So none of these are equal to 2. So none of these work by themselves as a general solution. So instead, we will use a linear combination of them and hope that it solves this equation in general. And so this part I skipped over when I was being more abstract. So there's a system of equations that we can implement here, which I will get into just as soon as I erase what's on here. So one thing that we can check, so first of all, the type of solution we're looking for is something like this. A sub n equals some constant, c1 times alpha 1 to the n plus another constant, c2 times alpha 2 to the n. And by the way, this should be alpha 1, this should be alpha 2, and we just reject 0. If we were to try to include 0 in this linear combination, it would just be a term that adds 0, because 0 to the n is always 0, and that term will contribute nothing, so we just ignore that. So to then continue this, it's just c1 times alpha 1 is 5 to the n power plus c2 times alpha 2, which is 2 to the n power, should equal a sub n. So now we can check a couple of values here. There's system of equations that we can implement, n equals 0 and n equals 1. So what are the two equations that we have available to us based on these initial conditions? We can see a sub 0 equals 2, and that's supposed to equal c1 times 5 to the 0 power plus c2 times 2 to the 0 power, and this is just a0 equals c1 plus c2, because 5 to 0 and 2 to 0 are both 0, are both 1, sorry. And a sub 1 equals 1, which equals c1 times 5 to the first power plus c2 times 2 to the first power. And that's just going to be a1 equals 5c1 plus 2c2. And sorry, I shouldn't have kept it as a1 and a0. This is a0 equals 2 and a1 equals 1. So now we can do elimination. We can say here that 4 by multiplying by 2 on both sides equals 2c1 plus 2c2. And then if we subtract that equation here, subtract 4 equals 2c1 plus 2c2, we get that minus 3 equals 3c1. And let's clear up a bit of space somewhere. So minus 3 equals 3c1, divide by 3 on both sides, and you get that c1 equals minus 1. Then you can plug that in here, and 2 equals minus 1 plus c2, and if you add 1 to both sides, 3 equals c2. So maybe there's one thing that I shouldn't have erased, which is where these values of c were supposed to be plugged in. But the initial goal was to have a sub n equals c1 times 5 to the n plus c2 times 2 to the n. And so now this means that a sub n equals minus 1, so we can just put a minus sign, times 5 to the n, and c2 is 3, so plus 3 times 2 to the n. So this is the explicit formula, and you can see that it doesn't require knowledge of any terms before a sub n. There's no a sub n minus 1 or a sub n minus 2 here, and this is a general solution. So we should check to make sure that this is correct by comparing it to what we would have gotten just using this recurrence relation in the first place. Let me just adjust the camera a bit. So a sub 0 is 1, a sub 0 is 2, a sub 1 is 1. We can even check those first. So a sub 0, using this formula now, equals minus 5 to the 0 plus 3 times 2 to the 0, and that's going to be minus 1 plus 3, which is 2, which is correct. Then we can do a sub 1 equals minus 5 to the 1 plus 3 times 2 to the 1, which is minus 5 plus 6, which is 1, which is also correct. To check any higher values, which we should do because we specifically solve the system equation so that those two would be correct, we should check higher numbers. So to check higher numbers, we also have to solve it using recursion. So first we can do a sub 2 equals 7 times a sub 1, which is 1, minus 10 times a sub 0, which is 2, and that's going to be 7 minus 20, which is minus 13. And we can check that here as well. A sub 2 equals minus 5 to the 2 power, 5 squared, plus 3 times 2 squared. That's minus 25 plus 3 times 4, which is minus 25 plus 12, and that is minus 13. So this also matches. And this at least suggests that in general, a sub n with this explicit formula is going to be equal to the recursive formula. So this is what it means to solve a recursive relation. And recall that the method for doing this was just to guess that there is some alpha such that a sub n equals alpha to the n. And then use a linear combination of the values that come out of that polynomial equation. And I've so far given no justification for why this is true, But there is a nice way to look at this using linear algebra, and specifically, eigenvalues are often useful for essentially having terms that are raised to the nth power. You may have seen that if you have taken a linear algebra course. And so I'll be going into how exactly that works. If you're interested, it is definitely worthwhile to try this on your own first. Try to see how you can maybe reflect a recursive relation and an explicit solution using linear algebra, using matrices and eigenvalues, and yeah, see if you can come up with the method you could use with linear algebra to demonstrate why this might be true. I will be going through that right now, but pause the video and try to think about it for yourself a bit, if you would like. Okay, so I already mentioned, so I guess I'll give a few hints and suggestions as to where we're going, and maybe if you haven't been able to come up with the solution by yourself, not a solution, but the reasoning, the linear algebra behind this solution yourself yet, maybe these hints that I'll give first can help you with that. So I've already said that it's going to make use of eigenvalues. And so the first thing you might want to try to think about is, yeah, how can you make eigenvalues relate to the problem of solving recursive relations? And that was a challenge. It took me some time to figure this out. Pause and see if you can figure it out there, but if you can't, you can continue to the next hint. And this really should follow pretty directly from the first hint, but you're going to need some kind of square matrices. And this is because only square matrices, it's only with square matrices that you can talk about eigenvectors and eigenvalues in the first place. Now it's unclear at first what square matrices you might want to use, but I will be explaining what kind of matrices you can use. And actually I'll just mention it now. It's basically that this square matrix is supposed to in some way encode the recurrence relation. Let's just call that RR for now. And we'll see how that's possible to do in a little bit. And then you also will need to use a vector to encode the initial conditions. The first few values in the recursive sequence that allow you to then use the recursive relation going forward. So yeah, again, if you can use these hints to come up with it, that would be excellent. I think it's very valuable to think about this yourself so that it sticks with you better. It's definitely much more effective learning actively than passively. But I will go ahead and demonstrate the way this is possible right now. So one challenge that you might have faced if you did try to do this by yourself is you're trying to say that a sub n equals some linear combination of preceding terms in a sequence. And recall we wrote this before as c1 times a sub n minus 1 plus, I may choose a different color for my constant from now on because this black marker is fading. Let's use some red. So c1 times a sub n minus 1 plus c sub m times a sub n minus m. So there's just a number of terms here, and you're just adding constant multiples of preceding terms. And it might be hard to see how you can encode this in a matrix, because the output is just a single value. It's yeah, and it may be easier to see how you might encode initial conditions in a vector. So initial conditions would just be saying a1 equals something. Well, I'm not even going to write an equal sign, but you'll be given some value of a1, a2, a3, and if you need m terms, the preceding m terms, then you'll have to have m consecutive terms at the beginning to kick off this process of using a recursive relation. So what vector can have m terms? It would just be a vector that looks like this. I actually probably start at a0 and go up to a sub m minus 1. That's m terms, and we can have an a0, a sub 0, and then a sub 1, a sub 2, going down to a sub m minus 1. So that encodes the initial conditions. How can you use this to then, what matrix can you use applied to this initial condition, this set of initial conditions, to then utilize this recursive relation? This is an interesting question, and the key that you have to realize is that you don't just want a sub n as your output. It's just not useful to do that. Instead, what you want as your output is you want to go from this set of conditions, a sub 0 through a sub m minus 1, and instead of just having a sub, in this case you want the next term, and the next term would be a sub m, not a sub n. Instead of just having a sub m as an output, you want to instead just move everything, the index of every value in your vector up by 1. So what does that look like? It would mean you then have a sub 1, a sub 2, going up to a sub m. And so this allows you, if you have a matrix that can take you from this vector to this vector, then that is encoding the recurrence relation, because it makes use of all the preceding terms, all the number of preceding terms that's required. It gives you the value of the new term, term in your sequence, and it also can be applied to this new vector to attain the next term, because once you apply this again, it should give you, like this, it should give you a sub 2 all the way down to a sub m plus 1. So what matrix allows you to do this? So let me erase this. And so we're trying to find a matrix that you can multiply, and we can call this matrix A. A times this initial conditions vector should give you a new vector, which is just the terms in the sequence bumped up by 1 index. And I should pause for a moment and say here that this may be starting to become unfamiliar for people who haven't seen any linear algebra, and the rest of this video will probably require a decent amount of linear algebra knowledge, but I will also try to make videos in the future which can provide that for you instead of you having to just have that knowledge previously. So we're looking for a matrix A that takes this vector to this one, and recall, like, a sub 1 is hidden here, a sub 2 is hidden in here, so you can see that like many of these terms are also here. So a sub 1 all the way through a sub m minus 1, which comes right before a sub m, all of those terms are from here to here in this vector that's already here. So if we want to have a matrix that takes the value here and puts it here, the value here and puts it here, and just move everything up by 1, it will look something like this. So let's first focus on the first term. So if you're doing this matrix multiplication, it'll be a0 times the first term here in the top left, a1 times the second term here, and everything on going this way, and the sum of all of those will give you the term over here. And you want just a sub 1. So you don't want any a sub 0, you want one a sub 1, and you don't want any a sub 2, and you don't want any of the other terms, you just want a whole bunch of zeros over here. Now, you want a similar thing for a sub 2. A sub 2 is the third term here, so you want the third entry here to be a 1. Sorry, I accidentally wrote 3 because third entry, but it should be a 1. And then you have 0, and you just have a whole bunch of zeros again. and this pattern continues. You should make sure you understand why this pattern is continuing. And then for a sub m minus 1, which goes to the second to last entry, the second to last row here will be a whole bunch of zeros, and the last entry is a 1, and that matches with this a sub m minus 1 to make it the second to last entry here. But then there's one last row in this matrix, and we need that to be a sum of constant coefficients of these m terms, and it needs to give us a sub m. And so this is where you can really encode the equation that you would normally think of as the recurrence relation. And so to do that, we want c1 times a sub m minus 1, where we get a sub m minus 1 here. So that puts c1 as the term right here. So that's being multiplied by the preceding term. Then I'm noticing that it's a little bit blocked here, so let's just shift it a bit. That should do it. So c1 goes here, c2 goes here, and gets matched up with a sub n minus 2, a sub m minus 2 right here, and this goes all the way back. Eventually c sub m gets mapped with a sub 0 in this case. So that's c sub m right there. And so that matrix allows you, and by the way, there should be many rows in between here. It's not meant to be just exactly 5 rows, but that's all that fit here. And so this matrix here allows you to take the number of terms that you need for a recurrence relation and turn them into the next, you just bump the indices up by 1. And this last row is especially important for encoding what the recurrence relation is actually doing to get a brand new term that wasn't in the first vector. So the way you want to use this matrix, which by the way is an m by m square matrix, which encodes the recurrence relation, the way you want to use this is by saying the following. So let's again say that this matrix is A, and then let's say, well, let's just call this initial conditions vector A0 vector equals A1 vector. Let's call this A1. But then we'll say that A to the nth power, this matrix raised to the nth power, times the initial condition vector should give us the an vector. And this a sub n vector will have its first entry will be a sub n, its second entry will be a sub n plus 1, its last entry will be a sub n plus m minus 1. That's not super important, but you can see that essentially every time you apply this matrix, you increase the indices by 1, and applying it n times will get you the nth vector with entries. And that's also enough to give you just a sub n, which will just be the first entry there. So now where do eigenvalues come into play? So the situation that we're looking for is essentially we want A to be a diagonalizable matrix, and we'll only care about cases when that is true. And there are other examples, and I'll point out exactly what it means for that not to be true in this context. But for this video, I'll be focusing on cases where A is a diagonalizable matrix. And if A is diagonalizable, oops. If A is diagonalizable, that means that A has an eigenbasis. What that means is that any vector can be expressed as a sum of the eigenvectors of A. And in particular, let me erase some of this here. In particular, we will want to express A0, the initial conditions vector, is going to be a sum I equals 1 to m, and this is just, actually I won't write it like this for now, but essentially it's going to be a sum of, it can be broken up into eigenvectors of A. And so, actually I will write it exactly like that. A0 is a sum from I equals, let's use 1, m. So there will be m eigenvectors, because it's an m by m matrix. So I equals 1 to m of Ri, so that's just going to be some number, some constant value, times an eigenvector, Vi, of A. So Vi are eigenvectors of A, and each eigenvector will have an associated lambda I, which is an eigenvalue. So recall, eigenvectors and eigenvalues, it means that A times the ith eigenvector is just going to be a constant, lambda I, an eigenvalue, times the vector itself. And that's just what an eigenvector and eigenvalues are. So now this is where we get to the really useful aspect of what looking at linear algebra does for this recurrence relation problem, is it allows us to say that this a sub n, well, a to the n times a0 equals a to the n times the sum from I equals 1 to m of Ri times Vi. And that's equal to lambda 1 R1 V1 plus dot 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 plus lambda m R m V m. So and this is, recall, also down here equal to a n. And so in some way an contains the nth value of the recursive sequence, along with a number of other terms, but that's the one that you care about most. And oh, sorry, this isn't lambda 1, it's lambda 1 to the n. This is a big mistake that I made, so I hope that's clear. Raising it to the nth power each time you pull out a factor of the associated eigenvalue. And that's really the key thing here, is that this is where this is why in the method that was used earlier, you could assume a sub n equals alpha to the n. It's really for this reason that those alphas are acting like eigenvalues. And you'll see also that the polynomial that came out of that assumption is like analogous to the characteristic polynomial that comes when computing eigenvalues of a matrix. So yeah, essentially this is how that idea of having a linear combination of some number raised to the nth power comes into play from the linear algebra perspective. And from here, I think I will just give some examples to show exactly how this plays out. And essentially, like again, this is a sub n, a vector with a number of entries, but you can find the explicit formula by just focusing in the top entry for this and for all of the vectors in this formula, and then you would have a sub n, not a vector, and just have an explicit formula for that. But again, I'll go into more detail about that in a little bit. So let's do the same example as before. a sub n equals 7 times a sub n minus 1 minus 10 times a sub n minus 2. And look at what this looks like. Oh, and of course, we need the initial condition. A sub 0 equals 2, a sub 1 equals 1. So the initial conditions vector looks like this. A sub 0, a sub 1 is going to be 2, 1. And now we want some matrix A such that this gives us a sub 1, a sub 2. Sorry, that's better. So actually, let's make it more general, where we want A times a sub, yeah, I guess a sub 0, a sub 1 equals a sub 1, a sub 2. And given this recurrence relation, first we want A to take A1 and put it over there. So it's going to be 0, 1, and you can test that out and see why that gives us a sub 1 in the top row. And then we want 7 times the preceding value, so that goes over here, minus 10 times 2 values earlier, so minus 10 goes here. And you can see then that A times, well, let's just do it out. We have 0, 1, minus 10, 7 times the initial conditions are 2, 1. This gives us 2 times 0 plus 1 times 1 is 1. 2 times minus 10 plus 1 times 7 gives us minus 13. And so that means right here, this is a sub 2. And we can check that again. 7 times 1 minus 10 times 2 is indeed minus 13. So this is successfully giving us later values. And from there, what we want to do now is find the eigenvalues and eigenvectors of A. So to find the eigenvalues, so that's where I begin here. A equals 0, 1, minus 10, 7. So the eigenvalues are going to be found using determinant of A minus lambda I. This is something that, yeah, some of the linear algebra knowledge that is kind of a prerequisite for this video, I suppose. So that's going to be the determinant of minus lambda, 1, minus 10, 7 minus lambda. This is going to give us minus lambda times 7 minus lambda minus 1 times minus 10. And after this step, I'll show that it's equal to 0. We want this to be equal to 0. So this is lambda squared minus 7 lambda plus 10 equals 0. This should look familiar. This came up also when we were using the method originally with alpha and just assuming that there was some alpha such that a sub n equals alpha at the end. And again, this is really just like an equivalent of finding eigenvalues without knowing that you are finding eigenvalues. So this gives you lambda minus 5, lambda minus 2 equals 0, and so lambda equals 5 or lambda equals 2. So this is lambda 1, lambda 2. From there, we can find the eigenvectors. So first, we have to talk about the eigenspace of lambda 1, which is E sub 5, because 5 is the value. So this is going to be the kernel of a minus 5I. Again, this is just from linear algebra that I hope you are already familiar with. And this gives us minus 5, 1, minus 10, 2. And that's, you can do row operations and preserve the kernel. So this is the kernel of, you can just subtract, subtract the first row times 2 from the second row, and everything cancels, so you end up with this. And if you say this row is x1, this row is x2, we can use a parameter x1 equals t, then x2, if we're setting this equal to 0, x2 minus 5x1 equals 0, x2 equals 5x1 or 5t. And so in general, the vector x1, x2 is going to be t times 1, 5. And that means that E5, this eigenspace, that's a little too far. E5, this eigenspace we're talking about, is equal to the span of 1, 5. And that's an eigenvector, 1, 5. Next, we can do the same thing for E sub 2, which is the other eigenvalue. E sub 2 being the eigenspace associated with that eigenvalue. And this is going to be kernel of a minus 2I, which is going to be kernel of minus 2, 1, minus 10, 5. Sorry, that's very blotched by the stuff that I couldn't erase earlier. But essentially you can subtract the first row times 5 from the second row, and again everything cancels, so you end up with minus 2, 1, 0, 0. Now, if you say x1 equals t, then x2 plus minus 2x1 equals 0, or x2 equals 2x1, x2 equals 2x1 and x1 equals t, so that's just 2t. So in this case, the solution is t times 1, 2. And so E2 is the span of this eigenvector 1, 2, and so these are the two eigenvectors. Now, what we want to do is show the initial condition as a sum of multiples of these eigenvectors. So the initial conditions, I forgot to write them down. A sub 0 equals 2, a sub 1 equals 1. Yeah. So to do this, you can write the eigenvectors as columns, and in an augmented matrix where you want to create 2, 1, and then you can do row operations. So let's 1, 0, so subtract 5 times this, minus 3, 5 times this is minus 10, so minus 9. This becomes 1, 1, 2, 0, 1, 3. And then from there, and subtract again. Just 1 times this, so 2 minus 3 is minus 1. And this minus 1, 3 means that A0, as I put earlier, which is 2, 1, equals minus 1 times 1, 5, which is one eigenvector, plus 3 times 1, 2, which is the other eigenvector. So let's check that this is accurate. It's minus 1 plus 3 is 2. That worked here. Minus 5 plus 3, minus 5 plus 6 is 1, which also worked. So now we want a to the nth power times a0, and that's going to be 0, 1, minus 10, 7 to the nth power times all of this. Actually, I'm going to create some more space. So a to the n times a0 equals 0, 1, minus 10, 7 to the nth power times minus 1 times 1, 5 plus 3 times 1, 2. And again, this is where the power of eigenvalues come in. So first of all, this is also going to be equal to a n. So this is going to equal lambda 1 to the nth power. Recall, lambda 1 was 5, lambda 2 was 2. So lambda 1 to the nth power times minus 1 times 1, 5 plus lambda 2 to the nth power times 3 times 1, 2. And plugging this in, this is going to be 5 to the n times minus 1 times 1, 5 plus 2 to the n plus times 3 times 1, 2. And that's all equal to a n, which recall is going to be a n, and since this is just 2 in anything, it's just going to be a sub n plus 1. So the top entry of this is going to be a sub n. And looking at just the top entry over here, that means that a sub n yeah, I need more room again. Yeah. A sub n equals, so looking at just the top component, it's going to be minus 1 times 1 times 5 to the n. It's going to be minus 5 to the n. And then here's 3 times 1 times 2 to the n plus 3 times 2 to the n. And this is the same solution that we got by using the other method. Obviously, this method is much more complicated, but it also allows you to see exactly where this method comes from. It's from writing the initial condition vector as a sum of eigenvectors, and then applying the recurrence relation matrix to that, and then the eigen values come out, and they're raised to the nth power. And that's why all this works. I said I would also do a Fibonacci sequence, but this video has gone way longer than I intended for it to, so I'm going to stop here. Thank you.